Okay, just courtesy notice that there were limit laws from way early in Calc 1 that the limit of the sum of two functions is the sum of the two functions limits separately, and there's similar versions of this for functions with two input variables like f of x comma y, g of x comma y. There are a number of these sorts of limit laws. Let's not, belabor these too much. I think what would be really neat looking forward is to do this. Write at least 5 ideas, concepts, theorems, whatever, that are related to limits from Calc 1. So kind of anything you want. For example, the derivative is defined in terms of a limit, so that's a freebie. But so if that's okay, of 5 things, just this is really just to get your mind kind of headed towards, yeah, what were limits good for in Calc 1? Because we're going to probably see a version of that here in Calc 3. Okay, in Calc 1, one idea that we saw with limit was continuity. And in fact, really the short version of the definition of continuity was this, that we said f is continuous at the input x equals a if the limit of the function as x approaches a equaled the actual value, right? Equaled f of a. Similarly, we can now define what it means for a function with two input variables, x and y, to be continuous. So we say that f is continuous at a comma b if the limit of the function as x comma y approaches a comma b equals the actual output, the actual z value, the algebra problem of f of a comma b. So as in Calc 1, polynomial functions are continuous, rational functions are continuous at each point in the domain, and so on. So if we're looking at the limit of x squared y minus 3xy squared plus 10 as xy approaches 3, 4, since this is a polynomial function we have here, we've got a continuous function, and therefore the limit is found just by plugging in 3 for x and 4 for y. Right? So this is what Stewart would have called the direct substitution property back in Calc 1. And so here's the work for that. Okay, recall that rational functions are continuous at each a comma b that's in the domain. So where is this function we saw earlier continuous? Well, it's just a question of what xy, what combination of xy is in the domain and what combination of xy is not in the domain. In fact, the only way you get no value is when we to the algebra problem here of like f of 2, 3, f of 2, 3 exists, right? The only problem would be if the denominator is 0, and the only way the denominator is 0, you've got x squared plus y squared. So keep in mind that those are never going to be negative. The smallest value you could have for x squared, if x is a real number, the smallest value of x squared is 0. So if x squared and y squared are both 0, in other words, x and y would have to both be 0. Right? So this is a rational function. Continuous everywhere except the one input, which is not in the domain. And that one input that causes a problem is the origin. That's the point when x and y are both 0. Right? So all of today's story, we're talking about limits of functions of two variables applies in the same way. We don't need to rediscuss all these things for the limits of functions of 3 variables. We're not going to do that. I mean, all of what you expect to be true would be true, right? So next time we're going to look at partial differentiation. It's derivatives, essentially, for functions of several variables.